Hello, good afternoon. It is a pleasure, and I am always grateful to be able to participate in this poster session for the Mexican Materials Society at this highly prestigious Congress. Today, we will talk about the topic of hydrothermal synthesis of zinc copper oxide and zinc nickel oxide nanoparticles for the photocatalytic production of hydrogen. This presentation is given by yours truly, Kelvin Gabriel Rincon Soto, affiliated with the University of Sciences and Arts of Chiapas at the Institute for Research and Innovation in Renewable Energies. Well, I will give a brief introduction. As we all know, the current energy models that we predominantly use are, in some significant way, fundamentally based upon fossil fuels. These particular energy sources have unfortunately poisoned our delicate ecosystems for many, many years, our precious skies, our vast oceans, leading us inexorably to a critical point of unsustainable crisis. Because of this, there is a constant and ongoing search for more environmentally friendly technologies or sustainable energy systems to enable a comprehensive transition toward being more eco-friendly. In this context, hydrogen steps forward as the fuel of the future. To obtain hydrogen, we need to use some kind of energy system. In other words, energy in whatever form allows us to produce it. That's why it's called an energy carrier, just like gasoline. There are multiple colors assigned to hydrogen. I won't mention many, just gray, blue, and green. This means that hydrogen is assigned a color to track how polluting it is. In this sense, gray hydrogen is the one that is produced, and during its production, since, as I mentioned, it's an energy carrier, greenhouse gases like CO2 are generated, along with other gases such as carbon dioxide and carbon monoxide. So any production that generates gray hydrogen is doing so because it is polluting with these gases. Blue hydrogen, on the other hand, is hydrogen where in some way the greenhouse gases emitted during its production are stored in certain reservoirs or are somehow captured. So that type of hydrogen is considered blue. And then we get to green hydrogen, which is the hydrogen that we generate using renewable energy or that we can produce through electricity by electrolysis. So we can call that hydrogen renewable energy, and that's where our research topic comes in. The emissions from its production are stored in certain basins or are somehow captured. So that type of hydrogen is considered blue. And then we have green hydrogen, which is the hydrogen that we generate with renewable energy or that we can produce through electricity by means of electrolysis. So we can call that hydrogen renewable energy. And that's where our research topic becomes relevant because we're interested in finding a green energy source through these renewable energies. And that's where photocatalytic hydrogen production stands out. Photocatalytic hydrogen production, as shown in figure number 2, requires a catalyst, energy, which can be either solar or artificial, and some medium. In this case, it's water with some sacrificial agent, but the idea is to take these investigations toward the degradation of the water molecule. For this, we need a semiconductor with the optimal characteristics to act as both a reducer and an oxidizer, and to handle the oxidation part. However, for this particular chemical reaction to effectively take place, photocatalysis specifically and crucially requires that each individual band edge possesses a very precise and optimal position within the energy spectrum. So on the reduction side, we absolutely need a minimum energy level of precisely minus 0.41 volts. And on the oxidation side, this particular energy level is exactly 0.83 volts. This means that thermodynamically speaking, the photocatalytic reaction is not favorable, so it requires energy in order to take place. Not just any ordinary semiconductor material can effectively generate photocatalysis. In theory, we specifically need approximately 1.2 electron volts of energy so that there is indeed sufficient energy available to successfully break the strong covalent bonds present within water molecules. That's why we need a band gap between 1.2 and 3.8. So we look for a semiconductor that is easily accessible, affordable, and non-toxic. That's why we are working with zinc oxide because it has these characteristics. It's quite environmentally friendly, it's affordable, and we can produce it in many different ways. In this case, we used 3.8. So we look for a semiconductor that is easily accessible, affordable, non-toxic, and that's why we're working with zinc oxide because it has these characteristics. It's quite environmentally friendly, it's inexpensive, and we can produce it in many ways. In this case, we used hydrothermal synthesis. Well, once the external energy is precisely applied, as you can clearly see next, if the applied energy is sufficiently great for its specific band gap, we effectively excite an electron from the lower valence band to the higher conduction band, thereby initiating a crucial electronic transition. So these charge carriers, the whole comes into contact with water or with some sacrificial agent, and we start to see the breaking of these bonds, right? So these bonds start to form hydrogen ions, which, when they move up to the reduction band and come into contact with the electron, become molecular hydrogen. And that's how we generate molecular hydrogen from the hydrogen ion. Both edges are necessary, one to break the bonds in the water molecule and the other to essentially reduce these hydrogen particles. We are using sacrificial agents because the sacrificial agent adds more hydrogens to the reaction in addition to filling the holes and serves as a sacrificial agent in this sense. Also, what we try to do with the hydrogen is to fill the holes to prevent recombination, which is so important in material science. Well, we also use some transition metal, in this case nickel or copper, which will help us prevent recombination. Well, the band gap of zinc oxide is 3.2 and it is highly attractive. The only drawback is that it responds to ultraviolet energy, which is only 5% of the available energy in the solar spectrum. That's why it's so important to add metals to improve its bands. What is the methodology used in this project? Well, we start by weighing our precursor, which is zinc chloride, dissolve it in water, proceed to the hydrothermal treatment, which is the autoclave part. Then we centrifuge, wash, dry, calcine, and obtain our material. So as a result, here we obtain our pure zinc oxide, but we still need to impregnate it with our transition metal. It's important to emphasize that our metal does not enter the structure of the zinc oxide. It's only deposited on the side, as could be seen in the image above. And well, once we have the zinc oxide, we prepare our metal salts with nitrate, copper nitrate, and nitrate Q. Why do we obtain our pure zinc oxide? But it's necessary to impregnate it, to impregnate our transition metal. It's important to emphasize that our metal does not enter the structure of the zinc oxide. It's only deposited on the side, as could be seen in the image above. And well, once we have the zinc oxide, we prepare our salt, metallic salts with nitrate, cupric nitrate, and nickelous nitrate. And we proceed to prepare the solution by incipient wet impregnation. We let it dry, then calcine it, and here we obtain zinc oxide with copper oxide, nickel oxide, and then we proceed to reduce it and thus obtain our nanoparticles of reduced zinc oxide copper and zinc oxide nickel. How were these particles evaluated? They were evaluated using a photoreactor in which ultraviolet energy with a certain wavelength is applied and a carrier gas is passed through, in this case nitrogen. We used a mass flow meter to quantify how much is entering and to direct it into the reaction. It's important for the reaction to be maintained in an inert atmosphere, since we don't want reactions or for our molecules to recombine with oxygen, forming water again or generating species we're not interested in. Well, once photocatalysis occurs, the hydrogen produced is sent to a mass spectrometer in order to quantify how much hydrogen we're generating and then process the data. The characterization equipment that we currently use includes advanced X-ray diffraction, precise UV visible spectroscopy, and the highly sensitive mass spectrometer. These instruments are employed to accurately determine the quantification, pardon me, in this particular context, for comprehensive analysis. The Riga-Komin spectrometer to determine the chemical composition. One of the first results we obtained was the X-ray characterization, which we performed on our powders to effectively determine whether we had obtained the material we were looking for. So as you can see, we actually obtained the 11 peaks of zinc oxide, which correspond to the structure or the PDF card 010749443, which is the Bursite type structure. So from there, we can see that in our first synthesis, we obtained a hexagonal Bursite type morphology without any impurities. Later, we performed synthesis on we did X-ray analysis on our already deposited materials, and these correspond to the structure or to the PDF card 010749443, which is the bursite type structure. So from there, we can see that in our first synthesis, we obtained a hexagonal borsite type morphology without any impurities. Subsequently, we performed synthesis on our, we performed X-ray analysis on our deposited materials, and we were able to see that we found the copper card 010703038, in which we can see peaks at the Miller indices 1, 1, 1, 2, 0, 0, 2, 2, 0, which match this crystallographic card. Subsequently, the smaller percentages due to instrumental error and the amount impregnated. Well, the diffractometer is a characterization method that doesn't help us to actually visualize it. But in fact, the equipment did detect the card, but no peaks are visible. The same thing happened with nickel at 3%. We were able to obtain the Miller indices, but at 1%, those peaks can no longer be seen, and the same goes for 0.5%. The trend is that the greater the amount of metal, the more visible these peaks are. So we can see that we obtained zinc oxide with the metal we wanted to deposit without any other material or any strange structure. All right, let's move on to the part where we calculate using those diffractograms the crystallite sizes, which are shown here in table 1. In this table, we can see that the zinc oxide, well, the crystal size was calculated using the Scherrer equation, in which we use the average peak width, the incidence angle, and so on. So we observed that a crystallite size of approximately 36.6 nanometers was successfully obtained. And as more metal was progressively impregnated, the crystallite size consistently kept decreasing, primarily because, well, the presence of the metal in some way is effectively causing the zinc oxide to remain a bit smaller. So copper also showed this same trend going from 56.7 to 55 and then to 34. The more impregnation occurs, the smaller the crystallite becomes. So those are the results we obtained there. And then we move on to the ultraviolet UV visible characterization, UV vis spectroscopy, where we were able to measure precisely in test A and in graph B. We measured the reflectance, well, the diffuse reflectance of the zinc oxide, where we can see that precisely in the pure part. Uh, ultraviolet UV visible, ultraviolet UV vis spectroscopy, in which we were able to measure precisely in both in test A and in graph B. We measured the reflectance, the diffuse reflectance of our zinc oxide, where we can see that in the pure part of the material, well, it reflects everything that is incident on it and shows a drop at the wavelength that zinc oxide absorbs, as reported in the literature, which is in the ultraviolet. And we can also see that as the material is impregnated, the reflectance changes. When 0.5% copper is impregnated, it actually absorbs less, reflects less energy, so it is absorbing more. And we can also see that there is a more pronounced drop in the zinc oxide. This means that even though the reflectance is indeed being modified, we are still within this ultraviolet energy range, since the amount of metal is too small to cause a significant change. The same thing happens with nickel, where we can see the same trend at 0.5, 1, and 3%, in which the material reflects accordingly. In figure number 5, once we performed the diffuse reflectance characterizations, the band gaps were calculated, which are practically very, very imperceptible. For example, for pure zinc oxide, we obtained a band gap of 3.22. For zinc oxide with 0.05 copper, we obtained 3.15, and successively with 1 and with copper, 3.18. So there were no apparent modifications, just very small ones, honestly insignificant. And we can see that for nickel, we also obtained 3.19, 3.19, the trend remains, and for the 3.12, which shows that there are no modifications in its band gap. It continues to respond to visible UV energy. I'll continue with the fourth characterization, which is X-ray fluorescence to determine the chemical composition. In the first sample, we found that it was exactly 79% zinc and 21% oxygen. Subsequently, it was impregnated with, which was 2, 1, and 0.5, where we can see that for 3% it was impregnated with 2.39, for 1%, 1.6, and for 0.5, 0.49. So we have a very acceptable percentage of the metal's mass percentage in the zinc oxide. The same thing happens in table 4. We have in the 3% sample, we have 3.43. For the 1%, we have 1.6. For the 0.5, we have 0.4. very acceptable percentages, and for nickel as well, a very acceptable percentage of the mass percent of the metal in zinc oxide. The same happens in table 4. We have A in the 3% sample, well, we have 3.43. In the 1%, we have 1.6. In the 0.5, we have 0.4. These are very acceptable percentages, and of the nickel we wanted for the transition. And once we obtained this material, we moved on to the last step, which was the evaluation, in which we could see that precisely in image A, the one that generated the most hydrogen was the zinc oxide with copper at 1%. These results are interesting because pure zinc oxide, as our hypothesis suggests, well, by adding this transition metal as a co-catalyst, the photocatalytic production would improve, and indeed, that's what happens. All the samples at 0.5, 1, and 3 surpass the hydrogen production. The same thing happens with B. The normal hydrogen, the pure zinc oxide, sorry, is still far below. So we can see that there is a trend here that even at 0.5 or 1%, the production remains insufficient. This is probably because at higher percentages, the active sites get blocked. So what we need is incidence, but with the metal present so that it acts as an agent, as an electron trap. So this has to do with the Fermi energy. The electrons go to the transition metal. There, well, obviously due to its energy levels, it retains them. So we can see that precisely the conclusions are that we have obtained a material that in some way generates hydrogen, and that by adding small percentages of nickel and copper at 0.5, 1, and 3%, the efficiency is improved with the most favorable results at 1%. So for this copper material at 1%, we obtained 96 micromoles per hour, and for the zinc nickel oxide, we also obtained very similar results. And for pure zinc oxide, well, 70 micromoles. So it's a quite acceptable conclusion, and well, that would be all from me. Thank you very much for your attention, and thank you very much.